Hello there, this is Professor Schmidt. Let's take a look at problem number 1 in this section about sex linkage of traits. Suppose you have two pure breeding lines of finches, one with orange beaks and the other with brown beaks. Finches are birds, I'm pretty sure you guys know that, but just in case. An orange-beaked female crossed with a brown-beaked male gives only brown-beaked sons and daughters. In other words, they're all brown-beaked. A brown-beaked female crossed with an orange-beaked male gives only brown-beaked sons and orange-beaked daughters. Explain these results. So they're basically asking us to figure out if this thing, what the dominant situation is, and since it's a section about sex linkage of traits, you might suspect sex linkage figures in there some way or another, but we have to see. So first of all, one thing that you need to know, and if you don't know this, the problem is ruined, is that birds don't have the same type of sex chromosome or sex determination system that mammals do, or even fruit flies do. Birds have a situation where it's called the ZW system. In a certain sense, it's the opposite of what we're used to, in that males in birds are the so-called homogametic sex, and that means that males are ZZ and females are ZW. We don't have to get into all the details of the ZW system, but we need to be able to, certainly to do the crosses correctly, we have to know who's homogametic, and it's the males. So now we can write down our cross. We've got an orange-beaked female. Now the W is similar to the Y in the sense that if there's a gene that's going to be sex-linked, it's going to be on the Z chromosome. The W is like the Y in that there's really not, it's not going to have the same map, it's not going to have the same genes on it as the Z does. So there's something that's sort of giving away the fact that, look, if you have a cross, and it's the second one in this case, if all the sons are one way, brown, and all the daughters are another way, orange, that tells you sex linkage right there. All right, so that tells you that it's sex linked, and it's on the Z for the same reason that if something's sex linked, we would assume it's on the X in the XY system. It's possible that it could be on the Y, but not likely. And if that was the case, it would come out in our problem solving situation. So we're going to make an assumption that this is a sex linked trait located on the Z chromosome and see where our crosses lead us. So an orange-beaked female, what would that mean? The female in this case would be Z, let's just make it up, Z, we don't know what's dominant and what's not now, so we'll call it, looks like a 2, but Z, O, and then she's W too, right? The male is brown-beaked, and he's ZZ, so we don't know if he's homozygous, heterozygous, etc. But one thing we do know is that his phenotype is brown. All of the offspring are brown in the F1 here. So that strongly implies, sex linkage or not, that brown is dominant over orange, right? If you mix an orange, if you cross an orange with a brown and all the F1 are brown, everything we've ever seen before leads us to believe that that means brown should be dominant. So before I'm going to rewrite this, but let's make some new terminology. Brown allele is going to be big B, and the orange allele is going to be little b, based on Mendel's convention. So let's now draw this out properly. It could all be wrong, you guys. I didn't look at the answer beforehand, but I'm just saying, if it makes sense, if this is not correct, we're going to find out when we attempt to do the problem. So now we're going to have an orange-beaked female, right? So she will be Z little b W, and a brown-beaked male. Actually, we don't know if, we just said, we don't know if he's homozygous or heterozygous, but let's try both. Let's say he's homozygous, and we'll do a Punnett square. So all the guy can make is Z big B, Z big B. Those look like 2's. Sorry about that. And of course the female can make Z big B and W. So these offsprings are going to be big B, little b, both of them in here. And those will be males, right? Brown males, which is what they told us we got. And Z big BW, Z big BW, these will be females, which will also be brown, right? So it seems our assumptions are correct. In really, if our assumptions are correct, that's the answer, that brown is dominant to orange and that it is sex-linked on the Z chromosome. But let's just check it out and see what if this guy was heterozygous, little b, like this, right? Get rid of this and make a whole Punnett square. Now we might find out that something different's going on here, because we really don't have to do this. Let me tell you the reason. We just got a situation which would explain the cross. A brown-beaked male, an orange-beaked female, and they got all brown offspring. So that might have been the homozygous, that might have been the cross that we just did. If we do it this way, the female still makes what she makes. The male can make big B or little b, so it's going to get a little bit more complicated. And you can see right here that if this was the case, half the males would be orange and half of them would be brown. So we now know, it doesn't, honestly, it really doesn't matter, but in this cross that they were telling us about, this doesn't disprove anything. It just means that they're giving us a situation. They didn't tell us, but the brown-beaked male that they told us about was homozygous, as long as everything else goes okay. Let's look at the other cross and see what we can make of that. And when I say the other cross, I mean this one right here. Sorry, right here. A brown-beaked female. So the female, again, remember, she's ZW. So using the terminology we have here, she's going to be like that, right? Because big B is brown. An orange-beaked male, this is good because there's only one way that could be, is if he's homozygous recessive, right? That gives brown-beaked sons and orange-beaked daughters. Let's see if it works. You know what? I want a bigger Punnett square box to write my results in. So the female can only make those, I apologize, you guys. Make this neat. She makes that and W. The male makes Z little b, and let's fill in the boxes. So we got big B, little b, big B, little b. So all the males here, right, are going to be heterozygous, but they are going to be brown. All the females, well, they're going to be ZB, little bw, Z little bw. All the females are orange. And is that what they said? Yes. Orange-beaked daughters, brown-beaked sons. This is like the crisscross inheritance that we have talked about in the theory videos. So pretty much this is an explanation of the results, and you can play around with it, and what I mean by that is make a different assumption. Assume that orange is dominant to brown. Try it out and you'll find out that it doesn't work no matter what you do. But on a test, what I'm telling you is you have to, well, you don't have to use shortcuts, and it's always good to verify things if you can. But there's two, just let me erase all of this over here. There's two things here which, without even doing anything, if you had less than 1 minute to answer this question, you would be able to make a pretty educated guess, right? When you see brown female or an orange male, and you see a crisscross with only brown-beaked sons and orange-beaked daughters, right then and there, sex linkage. That's number one, right? So we're saying that our gene of interest is on the Z chromosome. Of course, if you don't get the ZW part, that's why I mentioned, if you don't know that finches are birds, that's going to be a problem. But if you say, in the other cross, when you see a situation when you got orange and brown and you're crossing them and all the offspring are brown, that's a very good idea that brown is dominant right there. If you just had 1 minute and the test was almost over, you could say brown is dominant plus linked on Z. That is the correct answer, and we did it a little bit more detail than that, but that's what gets you started. You don't always get that, but in this case, it was a pretty good idea, and it turned out to be a correct idea. Question 2 asks, a pure breeding male fruit fly has brown eyes and long wings and is crossed with a pure breeding female that has red eyes and short wings. The F1 progeny are all red-eyed with long wings. Selfing F1 individuals produced the following offspring. And then they give us some data. So we've got 9 short brown males, 13 short red males, 36 long brown males, 74 long red females, 22 short red females, and 38 long red females. So that's a lot of flies there. Determine how eye color and wing length are inherited and the dominant/recessive alleles. And what was the genotype of the Generation P individuals? You guys, I probably said this before, but you might say, does he really have to read that whole thing? I don't really have to, but the reason I do is because sometimes if you're confronted with a problem like this, either on an exam or for homework, by the time you read all that, you're just like, I don't even know what's going on, and I'm not kidding. So I want to read it, get it all in our heads. I'm approaching it as I'm thinking that you might approach it. And then you have to sit back and ask, all right, I read it. What are they really telling me? And what are they really asking me? So personally, the things that would leap out to my mind would be, number one, we got pure breeding flies here, a pure breeding male, and they say it's pure breeding, having brown eyes and long wings. That means it's pure breeding for both of those traits. The pure breeding female has red eyes and short wings, so they're both pure breeding. Now, of course, a fruit fly can't be pure breeding in the same sense that one of Mendel's pea plants could be, because they can't fertilize themselves. But it means that if you have lines, that these came from a line where the males and the females, if you kept crossing those same ones together, they would always come out with these same results. And it does imply that there's some homozygosity there, as long as there's not sex linkage, or at least we would have to modify our idea about what it might mean if there's sex linkage involved. This part is about sex linkage of traits, but you may or may not be told that or know that for a fact if you got a question like this. So really what they want to know, 1, how is eye color and wing length inherited? So they're 2 separate traits, and when they say how are they inherited, they basically mean, are they autosomal or are they sex linked? And furthermore, even if they didn't write this, that probably implies that they want to know which is dominant and which is recessive. And lastly, what was the genotype of the original Generation P individuals? Okay, because we know the phenotype of them, that's what they told us. Now, a pure breeding male fruit fly, before we even look at the cross actually, let's look at the data and see what kind of ratios we're getting. But what you have to do is you have to separate the traits. So, in other words, first, forget about the color. Let's just think about the short versus long wings, all right? I'm going to circle all the short ones in blue. and all the long ones in red. And let's just forget about males or females, forget about anything. Not anything, but all we're interested in is in the short and the long. So if we add those up, even though I sort of wrote over them, it's 13, 9, and 22 gives you 44, I'll keep the colors, 44 shorts, and 36, 74, and 38. Doing it real quick in my head, but I think that's 148 long. Now, 44 times 3 is 132, and it's possible that I didn't do the math perfectly, but I think I did. 37, 74, 148. So a 3-to-1 ratio would be 132 to 44. We have 148 to 44. Really, it's close enough, at least for right now. And the other important thing to ask yourself is, all right, so let me just say this. If you accept that this is basically a 3-to-1 ratio, that means that long would be dominant, right? And short would be recessive. And that this came from a cross of the nature, if we'll make this big L and make that little l, right? Big L little l times big L little l, you know you're going to get a 3-to-1 ratio if you did a Punnett square for that, right? So right now we're going under the assumption long is dominant, short is recessive. Now, do you think it's sex-linked? And the way to know that is now to look at all the males and say, out of all the males, how many were short? So it's 22, just for the males now. We have 22 short, which is little l, and 38 and 36 is 74 long, right? Basically a 3-to-1 ratio. And we don't even have, there's only 2 categories of females here, 74 and 22. Look, they made the numbers identical. So the point of that is there's no difference between males and females. If it was sex-linked, one major way you'd know is that there was a difference in the ratios and data between the females and the males. So it looks right now that we just figured out one thing about the long-short allele, which is that we already wrote it here. Long is dominant, short is recessive, and this locus is not sex-linked. Another way of saying that is that it's not on the X chromosome, right? By the time we're done, we'll look at the crosses and make sure if it makes sense. Now what about, let's take our focus off of the short and long part and talk about the brown and the reds, right? One thing you could notice without even doing math is that out of the females, which are only these 2 classes here, all of them are red, right? So really, you don't have to do the math. Look at the males and you're going to see that there are some reds and some browns there, right? So that implies that the color locus is sex-linked. And furthermore, which one is dominant? Well, because all the females here are red, you'd be tempted to say red is dominant, and I think that's correct. Now, though, we want to look at the ratio in the males. So out of the males, how many reds do we have? 38 and 13, 51 red. And how many brown do we have? 36 and 9. We have 45. That's basically a 1-to-1 ratio. So we really don't get a lot of information out of that. But the fact that all the females are red tells us that probably red is dominant. And how do we want to say that? If red is dominant and it is sex-linked, we will usually show it on the X chromosome as X big R. It may or may not be wild type. I mean, you guys know that fruit flies have red eyes. That is wild type. But you can't really make any assumptions based on past knowledge when you get a problem like this. So we'll call it X big R, and we'll call brown being recessive X little r. So now we got to figure out, so this is still at the point of being a hypothesis or a proposition. If it's all true, it's good that they're asking us what was the genotype of generation P, because we'll do that cross and we'll see if what would be predicted is in fact the data that we've gotten, right? So extend the page a tiny bit. I don't want to lose track of where we were. So let's do the cross exactly the way that it would have to be based on everything that we've said. A pure breeding male fruit fly. So if he has brown eyes, brown we said is sex linked, right? So here's the male. Now he's X little r y, right? Because he only has a chance to have one X chromosome, he can only have one allele. So that's how the brown-eyed male is. He also has long wings, and long is dominant. Now, if he's pure breeding, that also implies very, very strongly that he's homozygous. In fact, that's why they put that in there, so you can make that assumption. So this is the genotype of the whole father, if you will. Big L, X little r, y. What about the female, the mother here? Well, she has red eyes, right? And since that is on the X chromosome, she has X big R at least. But the fact that she's pure breeding, again, that will strongly imply that she's, even though it's sex linked, remember in the females, there's two copies. So those are both going to be big R. But she had short wings, so she's little l. Remember, in this case, yes, she's pure breeding, so it's homozygous. But also, the only way to have short wings, since it's recessive, is to be little l. So now, if we go ahead and do this cross, we'll make a Punnett square, make a big one, and say, okay, what kind of gametes can... Well, actually, we may have, if this is like a dihybrid cross, right, I think we're going to have to do it separately. I'm sorry, it'll be fine. We'll do it separately. You could, in theory, make a giant dihybrid cross box, but when the X chromosome's involved, you know that you can, one's on the X and one isn't, right? We know that we can treat them separately. So first, let's look at the long and the short. The long and the short situation. All the gametes that the father can produce are going to be big L, right? And all the gametes that the mother can produce are going to be little l. So that says that all of the F1 offspring should look long-winged, but they'll be heterozygous, right? Heterozygotes, sorry. Now, we sort of lost track of this, but don't, because what we were looking at was data in the F2. The F1 were all red-eyed with long wings, okay? And we should have actually, we came probably to the right conclusion, but if we looked at this and we saw red with long, that would have implied right off the bat there's a lot of information here that red and long were the dominant ones. So now we're talking about the F1, just to be clear. We're going to have to go talk about the F2 in a minute. Hopefully there'll be room over here for us to do a cross with the X. So the father could make X little r and y, right? The mother only X big R and X big R. So let's see what that would mean. That would mean all the females look red and are heterozygous, right? All the males look red, and you can't really say they're homozygous or heterozygous, right? So in terms of just phenotype, everyone looked red in the F1 and everyone looked long. Isn't that what they told us? Red-eyed, long wings in the F1. Then selfing the F1 individuals. Now again, I should have mentioned, you can't self fruit flies the same way you can do it with peas. But what they mean by selfing is mating individuals from that same F1, the brothers and the sisters, basically. I know that doesn't sound appealing, but for flies, it's all good. All right, so now our cross is going to be that of the F1. All of the F1 males, all of them, are big L, little l, because everybody is big L, little l in the F1, right? Big L, little l, and all the F1 males with respect to color and the X chromosome, I'm sorry, I got a little ahead of myself there. They're going to be big X, R, and Y. So that's the males. The females are going to be big L, little l, because it doesn't matter if you're male or female, right? And they're all going to be X, big R, X, little r. So that's the cross that we now have to do. And it's not that bad. Again, we can keep it separate. So we'll do the long short over here. This becomes a regular heterozygote times heterozygote cross. And not too shockingly, we find out that we get a 3-to-1 ratio of long to short. And that's independent of the sexes, right? And let's just make sure that's what we saw. Remember, we did our little analysis up here. It's not an exact 3-to-1 ratio, but we said out of everybody, regardless of male or female, we got that 3-to-1 ratio, right? So far everything's looking good. This other cross is a little bit more complicated because it's X big R Y, X big R, X little r. So let's take a look here. And it's going to turn out great, you guys. So what does this tell us? All the females, while they're not all genotypically identical, they all look red, right? Because they have one big R. Is that what we saw up here? Yes. All the females were red. Now what about the males? These guys are going to look red, but these guys are going to look brown, right? And it's a 1-to-1 ratio, 50-50. Isn't that what we saw? That was this calculation right here when we looked at the F2 males, and we found that there were just as many red ones as brown ones. So it all makes sense. And really, just to reiterate, so what did they ask us? How are eye color and wing length inherited? Eye color is sex-linked, and red is dominant to brown, right? So let me put it in black here. That's the answer to the first question. Length of wings is not sex-linked, and long is dominant to short. What was the genotype of the original parents? Well, we see it right here, the parental. Big L, X little r, Y in the males. Little l, X big R in the females. And that's the parental generation. If they had asked us about the genotype of the F1, which they did not, we know that all F1 males look like this, and all F1 females look like that. So, it's a little bit lengthy, I'll admit, and there are some quicker ways to do it, but I think that we should take everything into account, make sure we're doing it correctly. If you're pressed for time, obviously you can try and speed it up a little bit. Question 3. For the following pedigrees, determine the mode of inheritance for the rare genetic disease: autosomal dominant, autosomal recessive, X-linked dominant, or X-linked recessive. So these are some pretty basic pedigrees. There are actually 4 of them altogether in this question. Just take a quick look. Looking down, they all only have 2 generations. And as we've discussed, if you've been watching the theory videos, it's very important to recognize this rare aspect of it. The bottom line is, if they say rare genetic disease, or it doesn't have to be a disease, but it often is, rare means that you can assume that someone coming from outside of a family is not a carrier unless there's absolute evidence to the contrary, or does not, carry the specific allele. So in solving these problems, sometimes you can just sort of see what you think is going on. But the most thorough way to do it is to do some detective work. And it's better to be able to rule certain things out than necessarily, quote, rule something in, because it's impossible to really rule it in. You got to get rid of all the other ones. So I like to first try and figure out whether something's recessive or not. And in this case, it helps very much to use, the letter A I like to use. So assumption one, let's say that this is autosomal recessive. And if it is autosomal recessive, then we'll assign genotypes to each of these individuals. So this gentleman would be little a, right? And we would know that any affected individual would also be little a. So the question becomes, could this individual, for example, get a little a from her father? Yes. But what about from her mother? In other words, could this mother be a carrier? In this case, only in one generation, we're assuming that these two people who got married or had children or whatever are not related. So we'd have to assume that she was not a carrier. So in fact, in that scenario, all of the offspring would have to get at least big A from mom, and that would mean that none of them could be affected. So we're going to say autosomal recessive does not make sense. What about sex-linked recessive? So if that was the case, this is tedious, but it works. The father would be X little a Y, right? Now, it is true that the father gives his X chromosome only to his daughters, so sex linkage looks attractive here. But remember that the mother also has to give one, and by the same logic we just used, she would not be a carrier. So again, the affected girls down here could not be getting two X's with the small a allele on them because they would need to get one from this parent, and they don't have it. So our second assumption, which I should have written down, would be X-linked recessive, and that's not working out either. So that pretty much means it's dominant, right? And we just have to figure out whether it's autosomal dominant or X-linked dominant. So I'm going to erase over here. Even going to erase this because we know it's not recessive now. So we got two choices left, right? Either it's X-linked dominant, because we know it's dominant, or it's autosomal dominant, right? All right, well, here's the thing. We sort of flip things around. If the father is affected here, we know if it's dominant that he has at least one big A, right? And what we know is that the mother here is little a. She comes from outside the family, but as well, she would have to be little a not to be affected by the disease, right? Now, we don't know. Well, let's think about this. If we're assuming that it's autosomal dominant, right, which I was, this is the situation. The father could not be big A, because then all the offspring would get at least one big A and they'd all be affected, right? So if it was autosomal dominant, the only thing that would make sense is for him to be a carrier, big A, little a, right? And if that was the case, if you do a little quick Punnett square, what you'd find is that about half the offspring should be affected and about half of them should not. And even though we see 2 out of 6, that's not completely unreasonable. So it's feasible that this could be an autosomal dominant trait, but the question is, let's look at the X linkage as well and see if that's just as feasible, and if we have to choose between the two, why we may decide that that would be more reasonable. Because if it's X-linked dominant, then the father is like this, and the mother is like this, right? Now, all males get their X chromosome from mom, right? And that would mean they're all getting X little a, and of course the Y from their father, and they would not be affected. All girls, fathers give their X chromosome to their daughters, right? So the only one he has is X with a big A, giving it to the daughter. Even if they got one with the little a from the mother, they're going to have the disease. So, look, you can't rule out autosomal dominance here, but X linkage makes so much more sense based on the sex ratio here, because none of the 4 boys got it, but all of the 2, if you can say that, girls did get it. So we're going to say here that if we have to choose, X-linked dominant makes the most sense. It's not impossible that it would be autosomal dominant. There's a certain probability this scenario would occur, but there's a lot greater probability of it being X-linked dominant. Okay, let's go to the next one. This one isn't so bad. It's a thing. It's a thing. What I mean is, we discussed, when we discussed the theory part of this, that if you see offspring, children, that have a disease and neither of the parents have it, we automatically know that it has to be recessive. What's the reasoning behind that? Let's just see if it was dominant, like autosomal. If this person had at least one big A, where are they supposed to get it from? If either of the parents had the big A, they would have the disease, right? And they don't. So that's not happening. And the same logic goes for X-linked dominance as well. It has to come from somewhere in the parents, and they don't exhibit the trait. So we know it's recessive. The big question here is it X-linked recessive, X-linked, or autosomal? Well, the best way to approach this is to, again, do a little detective work and to just say, could it be one? Could it be the other? So let's say it was X-linked. What would this mean? It would mean, aha, let's see if it's even possible. If the parents, for the parents both to be carriers, right? In other words, this guy right here, if this was an X-linked trait, he has to get an X chromosome, because remember it's definitely recessive, with little a and a Y, right? Now, the mother could certainly be a carrier in this way, so that would make sense. The father, though, would have to be like that because, sorry, the father would have to have a big A because he's not being affected by the disease, right? And the father would give that big A to all of his daughters, in essence protecting them from having the disease. So in this case, you literally can rule out X linkage, not even by any assumptions of rareness or things like that. It just is not possible because the father would have to have a normal X chromosome. We know that the disease is recessive, and he would have to give it to both of his daughters. That only leaves, of course, X-linked autosomal. But let's just make sure that that's going to make sense and it's going to be okay with the data. If it's X-linked autosomal, we can say that these individuals are both little a, and that simply means that they have to be able to get a little a from each of their parents. But the parents aren't affected, so they would have to both have a big A. And that's okay, it makes sense. I mean, the only objection I can think of, I hear you saying it, is if the disease is rare, how likely is it that 2 people would just get together? Well, I know, and it is unlikely, but say as in the case with cystic fibrosis, there is a certain probability that 2 strangers, if you will, both will be carriers of the gene. I mean, remember the rule, it's rare unless there's absolutely no other. It's rare, but you can assume that the person's not a carrier unless there's no other choice. Here, this is literally the only scenario that allows this pedigree to exist. So a little a is coming from there, and a little a is coming from there. So this one has to be X-linked autosomal. All right, this is fun. Now here we have a situation where both of the parents are affected and almost all of their children are affected. Almost. And I think that may be where the key lies, but we shall see. Now here's a question for you. Could this be recessive? if it was, let's say, start with autosomal recessive, the parents would all have little a's, and wouldn't that mean that all the offspring would have to just have little a's? And yet, this one doesn't. So you can forget about autosomal recessive anyway. Just to make sure, let's check out sex-linked recessive. If the parents both had it, this mother would have to be like this. The father would have to be like this. And again, even though the males get their X from their mother, right? They would have to all be affected, and this one isn't. So you can forget about recessiveness here. This is dominant. The question is going to be whether it's X-linked dominant or whether it's not. And you can drive yourself crazy sometimes by doing this. There's really no right way, but there's a smart way. And that is to say, look, whenever something's sex-linked, let's look at this person who's not affected, who happens to be a male, because we know he's got an X and a Y, right? So we've established that this is a dominant situation, right? So this person who does not have the disease would have to have X little a, right? And the question is, could he have gotten that from one of his parents? Well, where does a male get the X chromosome? He gets it from his mom, right? Is it feasible that she could be a carrier? Yes, that is feasible, in fact. If the father was X big AY, he's going to give the X chromosome to all of his daughters. So it is possible that we have an X-linked dominant situation here. On the other hand, let's look at what if it was autosomal dominant. If it's autosomal dominant, we know that this person is little a, right? And all the rest of these people have at least one big A. So this is sort of almost a reverse of before. Is it possible that both the parents are carriers in the sense that they're carrying the normal gene, right? If this is dominant, it's the big A that's causing the trait. But these two little a's could possibly get together, and they could lead to what would be a 1 in 4 chance of their offspring not, in fact, having the disease. So, like the first one, it could be X-linked and it could be autosomal. And if we have to choose one of these two, why would we choose it? Ultimately, we have to ask ourselves this. Since usually when you see sex linkage, you see some imbalance between the sexes, right? Here we have 2 males affected out of 3. All the females are affected. There doesn't seem to be a very obvious. Often with sex linkage, you're going to see more, sometimes almost exclusively males affected. We don't see that. This is a sort of an odd pedigree, I'll have to admit, with both the parents being affected. But put it this way, if it was autosomal, we'd have a 1 in 4 chance of any offspring, male or female, not being affected, right? And here we see, well, 1 out of 5 the children wasn't affected. So that makes a lot of sense. If we go back to the idea that it might be X-linked, let's just go back here and see. Remember, the father has to be like that. That's going to, well, you know, the more I think of it, and sometimes it does take a little while to think of it this way. We said that in order for this guy to get an X chromosome with a little a, the mother would have to be a carrier for, quote, the normal gene, right? But think about this. Since girls get 1 X chromosome from their father, they're going to always be affected. They're going to get 1 of the 2 X chromosomes from their mother. So they might be carriers or not, but there's no way to tell unless we see their children. See, this is getting a little bit convoluted. So the question is, if it was this situation, what's the probability that we would see what we're seeing? The probability is that about half of the males would be affected and about half of them would not be affected. So this really comes down to, guys, it could really be either X-linked dominant or autosomal dominant, but if you do it by pure probabilities, you would expect to see half of the males affected if it's X-linked, and you see a third. You would expect to see 1/4 of the total offspring affected, and you see 1/5. So this is 0.25, this is 0.20, this is 0.5, this is 0.33. They're both consonant, but this is closer. So if you absolutely were forced to choose one over the other, you should choose autosomal just based on the probabilities. But this one is really a tough one, and you could make an argument that it could go either way. And one of the reasons we put this one in here is, by the way, I don't look at these beforehand, so that's why it may seem like I'm going down different paths. But I think that'll help you more. And the reason is, if I just said, okay, this is what you do because I know what it is, you wouldn't see the thought process that's behind it. I'm doing detective work. I'm saying, well, what if this? What if that? That's the only way you can approach these, all right? But sometimes, they'll ask you which is more likely. Sometimes you'll be able to, like in this one, we were able to prove, basically, that it was X-linked autosomal. So we're going to choose dominant autosomal for this one that we were just working on. Definitely a toughie. Usually they wouldn't do that to you. Now in D, for the reasons we said before, right off the bat we can see that this is recessive, right? Why? Because offspring have the disease, neither of the parents have it. Now, what do you see right away? All the people who have it happen to be males. That's that implies strongly that it's sex-linked or X-linked. So let's see what would happen. We know the parents would have to be carriers to the extent they can be, right? If it's X-linked. And that means the mother would be X big A, X little a, because these guys have to have X little a and Y, right? Since we know it's recessive. If it's sex-linked, the father, not being affected, has to be like this, right? So he's going to give all his X with the big A to his daughters, so they couldn't be affected. And what about males? They basically have a half a chance of being affected, but the only people who can be affected are males. And that's generally what we're seeing here. So, looks good. The X-linked idea looks good here. What about the autosomal idea? If it's autosomal, these guys would be little a, and all it would mean is that the parents were carriers, right? Now, certainly, if this were the case, you'd expect that 1/4 of the offspring would be affected, and what we're seeing is that 2 out of 5, or 40% of the offspring are affected. That's not ridiculous. So we now again have a situation where you can't really 100% rule out one or the other. But what normally is said is that if only males are affected, because if this were the case, right, males or females could be affected, even opportunity. So the fact that 2 are affected is one thing. The fact that they are both males tips the balance towards the X-linked possibility. So we're going to say that this is X-linked recessive. My parting advice about these is, often with pedigrees that have more than 2 generations, some of them have 5, 6, or 7, you can find some place in there where you can rule one out. Here we just weren't able to do that, so we have to make our best guess. Now, best guess doesn't sound very scientific, and certainly you don't want to tell your professor, well, I just sort of guessed, I did my best guess. Often there will be more information that allows you to rule something in or out. Remember our the rare idea, but the rare idea didn't help us on some of these. It helps a lot on some other ones. So this is all. If this is what you're presented with, this is all you can do, and make your argument accordingly.
Question 4 states that color blindness is inherited as an X-linked recessive condition. A married couple, Joel and Julia, have normal vision, though both of their fathers are colorblind. What are Joel and Julia's genotypes? So let's define our alleles first. X I'm going to call just the normal X chromosome. And for the X chromosome with a mutant or colorblind allele, I'm going to call that X superscript little c. Okay. Now both Joel and Julia have normal vision. So for Joel, his genotype is pretty easy. If he was colorblind, that means he would have to be X little c y. But because he has normal vision, that means he's just normal XY. So Joel is just XY. And even though his father was colorblind, that doesn't matter in his case because he got his Y chromosome from his father and his X chromosome from his mother. Now for Julia, her colorblind father does matter. So she got one X from her mother, and she also got an X from her father. Now the only X chromosome that her father had the colorblind allele on it, so she is normal X and then X little c. And you also know that she got the normal X from her mother because she isn't affected, in which case she would have to have the allele on both X chromosomes. So these are their genotypes. Now for the subsections, it says, what is the probability that their first child will be a daughter with normal vision? So let's do a Punnett square to answer actually all of these parts. So let's see, Joel has a normal X and a Y, and Julia has a normal X and an affected X with the colorblind gene. So these are their offspring. Okay, so for A, what is the probability of having a daughter with normal vision? So the probability of having a daughter is 1/2. We've done that over and over again. Now, what is the probability that a daughter would have normal vision? If you look, these two, this one and 2, are the daughters of the offspring. Now this daughter, the first labeled one, has 2 normal X chromosomes, so she is not colorblind. The second daughter has a normal X chromosome and an X chromosome with the colorblind mutant allele. Now because it is a recessive condition, she isn't colorblind either. So the probability of a daughter having normal vision is 1 or 100%. So the total probability for A is just 1/2, which is the probability of having a daughter. For B, what is the probability of having a son with normal vision? So again, the probability of having a son is 1/2. And then if you look over here, these are the males in the offspring. This male has a normal X, Y, so he is not colorblind. However, this male, and because males are hemizygous, if you have an X chromosome with the mutant allele for a man, that means that they have this condition even if it's recessive, because they only have one X chromosome. So this male is colorblind. So the probability of a boy being colorblind is 1/2. So the total probability is 1/4. And again, I know we covered this a few problem-solving sessions ago, but just to reiterate, the reason why we say it's 1/2 for this and not 1/4 is because we're already setting this first condition that the child is a boy. So out of the boys in the offspring, it's only 1/2 is colorblind. So that's, and the same thing for here, is why we're not looking at both sides of the Punnett square. Okay, now for C, what is the probability of having a colorblind daughter? Again, 1/2 is the probability of having a girl, and because for conditional probability, out of the girls, none of them are colorblind, so that probability is 0. So then the total probability is 0. You can never have a colorblind girl with these two parents crossing. Now for D, what is the probability of having a colorblind son? So again, it's 1/2 for having a boy, and 1/2 chance of that boy being colorblind. So here's the colorblind male out of the 2 men. So again, that's 1/4. Question 5 states that a man with Menkes disease, an X-linked recessive condition that results in eventual deterioration of the nervous system, has a healthy daughter. This daughter marries with a man who is also healthy, and they plan to have children. So let's just take in consideration that Menkes is X-linked recessive. So for this father to have Menkes disease, that means he must have an affected X allele, so let's call that X big M, Y. And he has a healthy daughter. Now, it doesn't particularly matter what the mother's genotype is because you know that the daughter is healthy, so she must have at least one normal X because it's recessive, so she needs at least one normal X, and she has to get this other X from her father. So we know that this daughter is definitely normal X, XM. So this is the daughter. And she marries a man who is also healthy. So now she's marrying a man who is X, normal X, Y. What is the probability that a daughter will have Menkes disease? So let's do the Punnett square for this cross. This one here. Okay, so the father's healthy, so he has a normal X allele and a Y. The mother has one affected allele that she got from her father and another normal X allele. So if you see, these are the daughters here. Both have at least one normal X allele, and because this is a recessive trait, that means that none of the daughters will have Menkes disease. So therefore the answer to A is 0 probability. Now for B, it says what is the probability that a son will have Menkes disease? So if you want to look here, these are the male offspring. This one has a normal X allele, so it is healthy. But this one has the affected X allele, and because males are hemizygous, there's no such thing as a carrier male. And if you have this one affected allele, then you definitely have Menkes disease. So out of the 2 boys, 1/2 has Menkes disease. So that is the probability of a son having Menkes disease.